Hello, so I would like to describe for you today an electronics project that I've been working on. What you're seeing here is my media center PC, which I use for watching videos and also storing some files in some attached hard drives. Originally, this computer came in a very slim metal case which you can just barely see hanging off in the background here. And the only size fan that would fit into that case was extremely small, and it was not only very loud and on most of the time, which was not very good quality for a media center PC to have. It also was pretty inadequate at cooling. The processor was reporting temperatures in the high 70s, even 80 degrees Celsius, just at idle. So the fan was on 100% of the time and not doing a very good job of cooling the CPU and the rest of the computer down. So what I did was to build this wooden case, which, although it's much larger, has a lot more room, as well as a larger fan for better airflow. And so I've seen some pretty significant drops in the temperature that the CPU is reporting. But because of the way the motherboard was designed, I had to make a number of changes. First of all, the fan that came with the computer was a 5-volt unit, and this larger fan is 12 volts. And because this computer is essentially just a laptop board in a desktop case, the motherboard only has a 5-volt rail, no 12-volt rail. The power supply is 12 volts, but it gets converted to 5 volts almost immediately. I couldn't find a 12-volt switched supply anywhere on the board. So what I did to compensate for that was to build a little circuit using this white box that you see right here, which is a relay. Its coil gets activated by the 5-volt rail on the motherboard, and then it passes through a 12-volt supply that's wired directly to the power jack itself. So it sort of piggybacks on the switching capacity of the 5-volt supply on the motherboard to bring 12 volts to both the fan as well as to a USB 3.0 card that is on the underside of the motherboard and replaces the wireless card that came with the computer. Now, another change that I had to make was regarding the fan, was that the fan that came with the unit was a 3-wire fan. It had wires for the positive supply, ground, and then a third wire for the fan's RPM signal that gets fed to the motherboard. This fan is a 4-wire unit. It has those same 3 wires with the addition of a wire for a pulse width modulation signal, which is used to vary the speed of the fan. And let me show you a little crude diagram that I have here of what's going on. So this is a pulse modulated 12-volt signal. You can see that it's a train of square pulses at a nominal voltage of 12 volts, but because of these dips here where it goes down to 0 volts, the root mean square voltage is somewhat less than the maximum of 12 volts, and my understanding is that the speed of a DC motor is proportional to the root mean square voltage that it's seeing, although if I'm mistaken about that, as my understanding is pretty rudimentary, please feel free to correct me in the comments. So down beneath this, I have a signal here where the nominal voltage is still 12 volts, but the drops to 0 volts are much longer, so the root mean square voltage drops significantly. So the fan, in seeing a signal like this, is going to spin a lot faster than a fan seeing a signal like this. But because the motherboard of the computer was built for a 3-wire fan, I had to design a circuit to create the pulse width modulation signal that's now getting sent on the 4th wire of the fan. And what I used to do that was a PIC 12F683 microcontroller. I'm going to show you another crude diagram right here. It's a description of the circuit that is in this little board right here. Excuse me. Okay, so in the middle you can see the PIC. It is an 8-pin microcontroller. Pin number 1 sees positive supply, it's 5 volts. Pin number 8 is ground. This right here is an LM35 analog temperature sensor. It has a range of 0 to 100 degrees Celsius, and for each degree Celsius change, the LM35 outputs an additional 10 millivolts along its voltage output wire. So it goes from 0 volts at 0 degrees Celsius all the way to 1 volt at 100 degrees Celsius. That's fed into pin number 3 of the PIC, and then the PIC does some math both to calculate the duty cycle of the PWM signal, which is to say from 0% duty cycle when there's nothing going along the PWM wire to the fan, to 100% duty cycle where the fan's motor is seeing the full 12 volts and is running at full speed. I've also used the PIC to actuate a MOSFET that is acting as a switch to open the ground circuit on the fan's motor. Essentially, it just cuts off the continuity between the fan's ground wire and the ground plane on the on the computer's motherboard. So the PIC is set to send a signal to the gate of the MOSFET at around, I think it's 25 degrees Celsius, because if the computer is running at anything less than that, or rather if the ambient temperature that the computer is seeing is anything less than that, it doesn't really make sense to have the fan running. So at anything above 25 degrees Celsius, there's continuity in the fan's ground circuit, and the motor runs. Then at pin number 5 here, this is where the PWM signal comes out. It's a 25 kilohertz signal, so each one of those voltage drops is happening at a frequency of 25 kilohertz, which is the specification for 4-wire fans as set forth by Intel in one of their white papers. And so what the PIC does is to calculate the duty cycle based upon the voltage it's seeing from the LM35 temperature sensor. It goes from 0% duty cycle at around 25 degrees Celsius up to 100% duty cycle at 40 degrees Celsius and above. And with this design, I have seen pretty major drop in the temperatures that the CPU is reporting. It went from, high 70s to 80 degrees Celsius at idle to around the high 50s, which, while it's still high for a desktop computer, is really pretty good for the mobile CPU that is in there. And, the computer is functioning fine, and I'm hoping, at least, that I get extended lifetime out of this computer as compared to what it would have given in its stock case. Although even if I don't, and I really don't have any way of verifying, the project was fun enough in and of itself, I think, to warrant taking it on. So let me show you now how the fan speed varies in relation to the temperature. So the computer is currently off. When I turn it on, you'll see that the fan is going to speed up momentarily and then settle down into a low idle speed. Sometimes it sort of revs like that. It's not a cause for too much concern. It just, sometimes the signal from the LM35 is a little bit erratic. You can see this is where the LM35 is located. It's sort of just jammed into the fins of the CPU heatsink. So it's not in a perfect position to get a great temperature reading from the CPU. Certainly it's not tapped directly into the motherboard and getting the signal that the CPU itself is reporting. It's just sort of inferring from the ambient temperature what the temperature of the CPU is. And it works pretty good. As I said, at idle, it's high 50s degrees Celsius. All right, let me take you in a little bit closer so you can hopefully hear the fan speed up as the computer heats up. So you should be able to hear every so often the fan speed kicks up a little bit. Right now this is probably about 75% duty cycle or so. Alright, I'm going to replace the top of the computer before the CPU heats up too much. And now you should be able to hear the fan slowing down as the CPU cools off and the LM35 voltage output drops. So now it's dropping back down to the level that it usually sits at when it's idle. It's quiet enough that it's much more pleasant to to watch a movie now. You won't hear the fan whirring like a little hurricane in a teapot anymore. I think it was a pretty good improvement, and it was certainly a lot of fun to work on the circuit. If you have any questions, please feel free to ask me in the comments, and I will answer them to the best of my ability. In particular, if you'd like the source code for the microcontroller, which is written in C, I can send that along to you. Also, before I end the video, I just want to give a brief credit to Alan Parekh, whose website I've linked in the description box. His pulse width modulation controller was the inspiration for this circuit, and in many ways is very similar. There are a few notable differences. He uses a microcontroller which does not have a PWM module, and so what his does is to create the PWM signal directly on the fan's 12-volt supply, which is appropriate for a 3-wire fan, and I guess would also work on a 4-wire fan, although I think it's probably preferable to do it as I've done it. So again, if you'd like to hear more about the project, I'm more than happy to supply any insight that I can. Thanks very much for watching.